Hi, welcome to another week of our online 1212 lab here in North Georgia. I'm Dr. Meyer. This week we're going to be taking a look at Le Chatelier's principle and really the idea of chemical equilibrium. And so what we're going to be kind of taking a look at, the lab itself actually isn't too terribly long, but there's a lot of kind of like a theory aspect to this that we want to kind of understand and make sure hopefully you guys are thinking about as you kind of see the different components of the experiment. So we have three main parts of the experiment, three real reactions that we're going to take a look at. So we'll kind of break things down here into each of the three parts, basically, or each of the three reactions individually. But some general things here as far as setup, and then I'm going to kind of change some camera angles so you guys can see colors a little more clearly, because that's really going to be the focus of everything today, is looking at color changes as we make different adjustments to our equilibrium mixtures. And that we can use that then to get information about our reactions and kind of what's happening. And generally, we're going to be doing all of our reactions just kind of small scale in one of these little well plates. We have different kind of dropper bottles with all of our reagents for the reaction itself, and then also the kind of added pieces that we're going to be adding to our reactions to see what happens to our equilibrium as we make those adjustments. And then I do have an ice bath and a hot water bath over here as well, so we can take a look at how temperature changes things also. Because for each of these different reactions we're going to take a look at, we're basically going to have colors associated with the reactant and product sides of the reaction. And then we're going to basically make some change to that equilibrium and just observe what color change happens. And that color change should help indicate, oh, if the color changed to the side that indicates products, that means we just made a bunch of products from whatever we just did to our reaction. And it gives us information about what's happening. So it'll make a little more sense, I think, maybe as we look at some of our first examples. But that's kind of what we're going to be looking at throughout this entire experiment, is the colors as we make all of our changes. All right, so for the first reaction we're going to take a look at, we're actually going to be taking a look at the dissolution of sodium hydrogen sulfate. We already have a solution of it kind of pre-made that we're going to start with, so I'm just going to go ahead and add this kind of quickly to a few of the wells on our well plate here. And again, our goal as we make our observations is just to really see how things change. Most likely it's going to be kind of a lightening and darkening of colors. Most of the time it might not be a huge color change. Sometimes it might be a huge color change, it's really obvious. So we just want to pay very close attention and kind of really try to make good observations on things as we kind of watch them. So I have my wells that I've now filled with our sodium hydrogen sulfate, and the equilibrium we're looking at is just that dissolution, right? Sodium hydrogen sulfate breaking up to H3O plus and the sulfate ion, and we're going to kind of track the progress of that reaction using an indicator called thymol blue. And so I'm going to take and add a single drop to each of our three wells that I have right there, and then I'm going to go ahead and mix this up a little bit. So I'm going to mix this up and stir this, and we should see a color. It looks like it's actually staying kind of dark. So it's maybe slightly darker than we originally expect. Normally we'd expect maybe kind of like a reddish orange color. Looks more like we have almost like kind of like a red purple color. So it's pretty on the dark side right now, which is perfectly fine because again, we're really curious about color changes. The only thing that might come with this, any shift towards the product side, which is the more red side of this reaction with this particular indicator, we might not see much of a change. So if we don't really see much of a change, probably at least for right now, it's probably because we're shifting more towards the product side. We just might not be able to see it because of the indicator that we're actually using. Anything to the reactant side should see a pretty visible color change. So what we're going to do now that I've added our starting reactant and our indicator, I'm going to add some sodium sulfate. So sodium sulfate is on the product side of the dissolution reaction of our starting compound. And so if I add a product, we should expect things to kind of go backwards to the reactant side, which from our pre-lab kind of discussions and kind of an assignment, it should be more kind of a yellowish color, which at the very least should be a lighter color. So I'm going to add a few drops of this, and right away you can already see its color starting to change a little bit. I'll stir this a little bit and then kind of try to get a good angle that the camera can see. But as I mix this up and stir this and kind of now look at it, this solution over here has now gone almost completely yellow. Right? So adding the sodium sulfate, it's gone a yellow color. We said the yellow color is more indicative of our reactant side of the reaction. So by adding a product, our reaction has gone backwards. That's kind of the change that we've seen. And so what I'm going to do kind of from here is for both this rest of this part of the experiment and our next reactions, I'm mainly just going to add the reaction component we're asked to add, observe the color change, kind of help you to figure out what color that we've seen. But then I'm going to actually let you guys kind of think about reactants, products, kind of what's been added, or what side reactions might we have caused that creates us to either make more reactants or products. I'm going to try to leave that a little bit more up to you guys as you're kind of going through this to think about, because that's really the point of this whole experiment. The experiment itself is going to go pretty quick as I get going, and it's really just that the kind of thought process to really help analyze and think about why we're seeing some of the changes that we're seeing. All right, so the right well here, what I'm going to do is I'm going to add some sodium sulfate. and we're going to see how its color changes. So I have some solid sodium sulfate here. I'm going to go ahead and add to that. And I'm actually going to give it a little bit of a stir. And it doesn't really look like we're getting a huge color change here, if any. And kind of what I said before, I think it probably is holding a little bit true here. Looks like it's actually having some trouble dissolving a little bit. I think what we're probably seeing here is the fact that it's not changing and lightening up. It's not going backwards to the reactants. But by adding our sodium hydrogen sulfate, we should expect that our color, by adding a reactant, probably should be getting a little bit more towards the product side. But if we're looking at our colors, we don't really see a huge change. If you look at CSE Pub, it's probably going to ask you, does the reaction go forward or backwards? In this case, we'd probably say it is going backwards. It's going towards the products as the darker color because it didn't go light like what we saw very clearly the first time. And so that would be how I would treat that particular one. And the last thing we want to take a look at is what happens with temperature. So this middle one that I haven't added anything to, I'm actually going to pull this up into a pipette and let this kind of drain down to the bulb if I can here. There we go. And so now I have this liquid down here in the bulb. And what I want to see is what's going to happen to this as I heat or cool this down. So I'm going to stick this in a hot water bath for a few minutes, a couple minutes. And then what I'm going to do is I'm going to bring it back over here to show visually what it looks like after the hot water bath. And then I'll do the same for the cold water bath. All right, so here we are a couple minutes after heating. It looks like it's a little bit red in color, but at the very least, in comparison to where it started out, it looks like it has lightened some. So it's maybe not quite as fully yellow as what we saw before, but it's also not as dark, deep purple as what we kind of started out as. So to double check and see that heating the reaction made it go towards the reactant, similar to like what our first step did, I'm also going to put this in an ice bath. So what I'm going to do, I'm going to have to bring the ice bath kind of on screen, that's fine. And I'm just going to kind of submerge and hold this in an ice bath for a couple minutes. Again, I'm not going to videotape the whole process where you have to sit and wait. I'll show you guys kind of the clip here of after a couple minutes what this looks like, just so we can see what the color change looks like after. All right, so at this point, this thing's been in the ice bath a couple minutes, so I'm going to go ahead and pull this out. And if we're looking at our color here, it looks like it's gotten darker again. It looks like it's kind of similar to our starting kind of color that we started out with. And just to give a good contrast, I actually went ahead and made some more and put in the hot bath so we can have a bit of a color comparison here and just actually looking at them. And it's not a huge color difference as we're looking at them, as I'm trying to spin these in some different angles for our camera to kind of see. But this one that I'm holding here is hotter. This one was colder. The hot one is lighter in color. It's a little more reddish orange as opposed to kind of purple red. So the lighter color is tending towards the reactant side. So that means adding heat did make this reaction go towards the reactant side of our reaction. And we can use that then in our kind of observations and kind of conclusions then later. All right, so for the second part of our experiment, we're going to be taking a look at the equilibrium that involves magnesium hydroxide as a solid, dissociating into magnesium 2+ and hydroxides. So just the general dissolution reaction with magnesium hydroxide. But we're not going to start with magnesium hydroxide itself. We're actually going to make it by reacting sodium hydroxide and magnesium chloride, which if you kind of think back to Gen Chem, this is really kind of a precipitation reaction. So I'm going to add some magnesium chloride to each of my wells here to get started. And then what I'm going to do is after I've done that, I'm going to add sodium hydroxide to each of them. And hopefully what we should see is kind of a white solid precipitate form. That white solid precipitate that we see form when we mix these two should be our magnesium hydroxide solid. And then our other changes we can use to help us figure out what's happening to our equilibrium. Kind of getting down to the dregs of magnesium chloride solution here. Should hopefully be enough still to see everything. And so what I'm going to do now is add a little bit of sodium hydroxide to each of these. And you see it getting a good bit of white precipitate to form. That's what I want to see. So all of these have quite a bit of white solid that is now formed. And I'll kind of tilt this, the well plate to the camera to have a little bit better view. Very white, cloudy solutions that have now formed in here if I mix them all up. There's a bunch of white particulate kind of both floating at the top and just kind of throughout the whole solutions. So now what I want to do is actually kind of do with our procedure assays to take a look at, which is adding some different components. Now, unlike our first equilibrium where we were really adding like reactants and products, now we're adding things that are a little bit different, right? So the first one we're going to take a look at is concentrated hydrochloric acid. All right, so we want to know what is the concentrated hydrochloric acid going to do to our reaction. So I'm going to add a few drops of this to our, is that kind of smoke a little bit when I open it? How we know it's nice and concentrated. And as I add a few drops to this first well, right away you can kind of notice the well starting to clear up some. Right? Our well is not nearly as white as it was previously. So we can tell that our concentrated HCl, what it's doing is actually helping to dissolve our solid product. So adding HCl, it's doing something in our reaction to get rid of the solid, and I'm going to leave the rest kind of to you guys to look at and kind of make your correct observations and conclusions from. And the other change you want to look at in the second well then is by adding EDTA. So I'm going to add some EDTA to the second well. And as I add it, it's not happening quite as quickly as it did with the hydrochloric acid, but I'm getting a very similar effect, especially as it sits there for just a little bit. Now if I mix up my solution and look at it from above, it's not all the way clear, but if I give this some time and probably add some more EDTA, it will eventually get to be clear, like with the one that I added the HCl to. It's nowhere near as cloudy and thickly white as the other solution that we kind of started out with. So that's kind of the big thing that I wanted to highlight there. Both HCl and EDTA have a similar effect in that the white solid is going away. And if we think about what that means for our equilibrium, if our equilibrium was magnesium hydroxide as a solid going to magnesium and hydroxide ions, that white stuff that we see is the initial reactant, right, the magnesium hydroxide. So if it's going away, adding these things does make us go towards products, but you want to think about why that is. I'm going to leave the explanation part to you guys as you kind of put together as you're going through your lab. Now, the last part of this, we're actually going to add something called phenolphthalein. This is a visual color indicator. And so I'm going to add a couple drops of phenolphthalein to this solution. And phenolphthalein is an indicator that turns pink in the presence of base. So if there's a bunch of hydroxide ions in solution, we're going to see kind of a pink-purple color. And that's what we see right here. And so what I'm going to do now is kind of similar to the first part of the experiment where we did kind of the temperature examination. I'm going to take this up into a pipette. So I'm just going to pull all this up into a pipette. And then I'm going to go ahead and I'm going to put this, let this all drain down a little bit. Try not to spill too much of it on myself. It's not stuff you really want to be touching. Honestly, probably should have gloves for this. But here, if I have this solution, now what I'm going to do is I'm going to take this and put it in the hot water bath. And I'm going to see how this color changes. So we have kind of this nice pink color right now. We're going to see, does it get darker purple, which would mean kind of a more intense hydroxide concentration, or does it get lighter in color as we heat it up? All right, so I'm back now after having heated this for a good bit. And as, again, a way to try and give a good comparison, I've also tried cooling one down at the same time, the same kind of mixture. And I think this gives a better kind of visual comparison. The one I'm holding here that you see right here, this was the one that was in the hot water bath. It's a much lighter color, which indicates that there's much less hydroxide here. The one that's the colder temperature, the one that's just been sitting in this ice bath right here, is a darker color. That means there's more hydroxide in that solution. That's what that visual indicator that's in these solutions is helping to tell us. And so you want to be able to use that to help figure out, well, which way is my reaction going? Right? Hydroxide's a product, so the colors here you can use then to figure out if this is less hydroxide. That's telling you whether you have more product, less product. You can kind of go and piece that part together yourself to help figure out if things are exothermic or endothermic. But that's all the demonstration part for the second part. We'll move on to the third reaction here now and show you the last little bits, and then we'll have a little bit of a wrap up. Right, so our last reaction we're going to take a look at here is going to involve a cobalt chloride compound that's dissolved in ethanol. That's the ALC abbreviation that you see on the bottle. Apologize for the glare that's there. And that's important because that means water in this reaction that we add is actually not the solvent, it's going to be a reactant. So we're going to take a look at what happens to this cobalt chloride compound when we add water. It's going to form a new complex, it's going to have a different color, and the visual color of the cobalt compound itself is actually going to help us figure out, do we have more reactants or more products? Because initially we can see reactant-wise it's going to start out this nice, pretty royal blue color, and then when we go to add water to it, we're going to see what happens as far as getting a color change. So I'm going to add some of our cobalt compound to each of our first couple wells here. And then what I'm going to do is I'm actually going to take just a pipette here to take just a couple drops of water into each of these. And we see that that blue color might be a little difficult to see, but the blue color has definitely gotten lighter. And if I actually stir this a bit, my guess is it's probably going to get a little bit lighter yet. In fact, there as I stir it, you see them actually go, might look even clearer, but they actually do have a slight pink tinge to them. So they have kind of a slight pink color, which that's the color of the complex these things make with water. And so now what I'm going to do to this first well is I'm going to actually add some concentrated hydrochloric acid. And again, I'm not going to explain whether that's a reactant or a product. It's not directly either, but it is going to have kind of an effect that's similar to adding a reactant or product. And as I add the HCl, notice instantly what happens. That color went all the way back to blue. Right? So that first well, adding the HCl, went to the blue color. That means adding HCl helps us make reactants. So that's an important part for adding the HCl. And then the other part that we want to take a look at is what happens if I add the silver nitrate. Well, the HCl just turned things blue. Now if I add the silver nitrate, I'm going to add it to that same well, I actually see a couple things happen. Right? So there's two things that are visually occurring here when I add the silver nitrate. One, I'm getting kind of that white chunky solid, right? You see kind of a whiteness to that solution that you didn't see before. And if you can see the solution, it is back to having a pink tinge to it. So adding the silver nitrate, unlike HCl, actually favors the pink color, which is our product side. But it also made this white solid. And so that white solid, I think, is pretty key to the equilibrium in terms of understanding what's happening. So if you go back and look at the written equation for this equilibrium in particular, that's in your pre-lab and in your notes, if you look at that reaction, it should hopefully make sense that adding silver nitrate is doing something that creates both a white solid and causes us to favor the products of that reaction. So kind of keep that in mind to help explain what's happening in that step. Now, the last thing I want to do, similar to what I've done in the other ones, I want to take a look at temperature effects. So I'm going to go ahead and pull some of this up into a pipette. It's not a ton, but should hopefully be enough for us to see a color out of. So there, because we're really just looking, is it going to be like kind of purple, or is it going to be like blue? That should be noticeable, or is it going to be this light pink color still? So I'm going to heat this up real quick, and then we'll take a minute or two here to see what happens. And I'll have one that I'll put in an ice bath here as well in a cold temperature for the comparison. All right, so here what I have is our solution that was in the hot bath. Here's what I just took out of the ice bath right here. And these two colors are very similar. Might even be hard to kind of differentiate them too much. But this one here that just came out of the hot water is very clearly a good bit darker. It's not blue by any means, but it is almost more kind of like darker tinge of almost purplish pink as opposed to the really light pink one that came out of the cold water bath. So hot water favored the bluer color. So even though it didn't convert everything over to that blue color, that's fine. It shifted it in that direction. So this is hot, basically the heat helped shift it back towards reactants, which was the blue color. Cold helped shift it towards the products, which was this lighter pink color. So that should be all of kind of just the visual demonstration of everything from this experiment. The rest is really going through and kind of understanding why some of these changes are happening. And hopefully you should be able to make sense for each of these visual color changes and all of the reactions that we've seen today and actually figure out, okay, why did it make that change? Always be kind of asking that question because Le Chatelier's principle is usually relatively straightforward. If you make a particular change to an equilibrium, you should see a particular kind of reaction from that equilibrium to get back to an equilibrium state when you've disturbed it. And so things like adding a reactant should always kind of push it towards the product side. Adding a product should always shift it towards the reactant side. Things like that should always be true for any reaction. So kind of keep that in mind as you're thinking about the changes that you see in this experiment and kind of trying to explain what you're actually seeing as you answer some of your CSE Pub questions. The last thing I'll make a note of, all of the waste from this lab does have to be specially collected if you're doing it in person. Probably a good rule of thumb, if there's colors to your solutions, probably not something you should be sending down a sink. And so that applies to pretty much all of the solutions we made today. So there is special waste disposal if we were in person that I do just want to kind of touch on a little bit. Safety-wise, you probably heard me mention earlier, wearing gloves to this lab, not a bad idea. Things like concentrated hydrochloric acid, probably don't really want to get that on your bare skin. You might have seen me even flinch a little bit earlier because I did get one drop of it on a finger. And that's something you obviously would like to avoid, but it's such a small amount. As long as you rinse your hands really good, which is what I did after our video clip, then it should be fine. Nothing's too terrible here in that regard. I will make a special note on silver nitrate, just for those of you that have never used it before. Silver nitrate, what can happen if you get it on your skin, you probably won't notice it right away. It doesn't hurt or anything like that. It's not usually like a big irritant unless you still get just a lot of it on your skin. Usually what will happen is after a day, it will probably turn your skin black. And so the silver can actually react with light in particular. So once you've been exposed to your sunlight or just enough regular light, that silver can react and you actually kind of black splotches on your skin wherever you spilled the silver nitrate solution. So something to kind of be aware of and be careful of. Long term, it's not super harmful. It will go, like the color will go away after a couple days, but if you ever work with silver nitrate in the future and notice you have like black splotches on your hand, and you're like, that should be a tip off, oh, I got silver nitrate on my hands. Like I said, might not see it right away, but something to think about in the future if you ever have to handle, because I'm pretty sure anyone going into organic, you'll probably see this reagent again. So it's just kind of something to keep in mind. But that's everything I have for this week. We will see you all next time.